Hello everyone, I'm from Renmin University of China. Today I'm pleased to present our paper, Hunting Bugs with Accelerated Optimal Graph Vertex Matching in ISTA22. In recent years, bug detection techniques based on code similarity measurement have proven to be very effective. Such approaches match a code fragment, such as a function containing a known bug, with the target ones to detect the suspects that are similar to it. The detected fragments are likely to contain unknown bugs similar to the seed. The code fragments are essentially a kind of graph and can be naturally represented as various graphs, such as CFG and PPG. These graphs are good representation of code structure. Therefore, many researchers will measure the code similarity based on graph embedding techniques. Typically, these methods embed the whole graph into a vector. However, these methods suffer from false negatives and false positives caused by a noise problem. In practice, the logic of a bug often involves only a few statements in the code fragment, while others are bug irrelevant and can be considered noise. If we encode the whole graph into one vector, the information of the noise code will also be encoded into the vector. As a result, the similarity measurement task will be heavily interfered with by the noise and lead to false positives and false negatives. A natural way to address the noise problem is to remove the noise vertices before embedding and matching. Actually, we can remove the noise in the seed in advance because the bug-related statements are often definite and can be identified. Unfortunately, we cannot assume there is a specific bug in the target code and mark the related statements to exclude the noise in advance, while only sanitize the seed cannot solve the noise problem. Here, we are shown a real example. Figure A involves a no bug. A crafted file may cause the parameter of function map copy to be a negative number and result in a heap-based overflow. And figure B includes a similar bug. While both functions contain hundreds of lines, the core logic involves only a few statements. Using A as the seed, the whole graph embedding techniques ranks B the 212th. Sanitizing only the seed makes its ranking even worse, 5031st. Neither could help the analysts identify the bug in Figure B in practice. We address the above noise problem by optimal vertex matching, namely, establish a one-to-one correspondence between the vertices in two graphs. The obtained matching should maximize the similarity between the matched vertices. The similarity here should include the first-order similarity, second-order similarity, and higher-order similarity. As shown in the figure, the graph similarity can be measured on the vertices of interest, that is, the bug-related vertices in the seed and their counterparts in the target graph. As a result, the noise vertices are excluded and the obtained similarity is reasonable. Because of the consideration of high-order similarity, the task is generally NP-complete, which will bring huge time overhead. Therefore, we design a two-phase approach to speed up the optimal vertex matching. Our basic idea is to complete the optimal vertex matching in two phases. The first phase estimates the matching score between graphs based on whole graph embedding and reduce the number of targets to be analyzed. The second phase calculates a more accurate matching result based on a graph matching model. Specifically, phase 1 is candidate filtering. Each graph is embedded into a vector. Based on the vectors, the matching degree between graphs is roughly measured, and a limited number of targets with high matching degree with the seed are quickly identified and filtered as candidates. Phase 2 is vertex matching. Based on a graph convolutional model, the high-order similarity information between the candidates and the seed is extracted, and then an approximate but accurate enough matching result is obtained based on this information. Matching. There is a code graph preprocessing phase. Firstly, the source code is parsed into statement-level graphs. Here, we extract one code feature graph per function by combining its CFG and PBG. Each vertex contains the intermediate statements corresponding to one source code statement. Additionally, we replace the variable names with their normalized types. Secondly, we use the BERT model to embed each vertex as a feature vector containing the semantic information of its statements. Here, we treat each intermediate statement as a token and each function as a sentence to train the BERT model. Then, in phase 1, we propose a vertex matching-oriented embedding model, VME. VME encodes the sanitized seed graph and target graphs to vectors and calculate a matching score between the seed and target. The score can be used to fast estimate the vertex matching degree between the two graphs. The higher the score is, the higher the matching degree between the target and seed. VM embedding module consists of a vertex embedding layer and an aggregation function. The vertex embedding layer is a multi-layer perceptual network with a gate structure. Although mean pooling is commonly used as the aggregation function in graph embedding models, we find it will completely mix the vertex information, and every dimension in the graph vector can be affected by the noise vertices. Here, we choose max pooling as the aggregation function, because max pooling can keep the dominant feature of each dimension. Meanwhile, instead of measuring the similarity between two graph vectors directly, we focus on only the dimensions which, in the seed vector, are greater than a certain threshold t. Those dimensions are extracted to form two new vectors that are used to calculate the matching score. Max pooling keeps the dominant feature of each dimension, but it also leaves the noise features in the resulting vector and makes even lower similarity. Filtering the dimensions based on the seed actually highlights the important dimensions and reduces the impact of the seed-independent noise as far as possible. The experiment shows that 0.02 is a proper threshold. To train the model, we construct a series of quintuples, each containing 3 graphs and 2 labels. Given a graph POS, which is randomly chosen from the target graphs, we generate a subgraph ACR from it. More specifically, take a random vertex of POS as the sentry, and include its k-hop neighbors to form ACR. Then we randomly sample another target graph as NEG. We set S1 to 1, indicating the satisfaction of optimal vertex matching between ACR and POS. Label S2 is calculated by the Hungry algorithm to denote the matching degree between ACR and NEG, and we employ triplet loss as the loss function to train the model's ability to identify a better match. In the second phase, optimal vertex matching is performed on the seed and canvas. To avoid solving the NP-complete problem, we build a graph convolutional neural network and name it High-Order Similarity Embedding Model, HSE. The high-order similarity between vertices is encoded into an affinity matrix, and then the Hungry algorithm is applied based on the matrix to solve the optimal matching. Besides, we apply an attention mechanism to the convolutional layer of target graph to suppress the noise propagation. Each chain example for HSE model is a triplet. Randomly select a graph from the targets as GW, and then slice a subgraph from GW as GS. There is a 1-to-1 correspondence between the vertices in the subgraph GS and the vertices in the original graph GW. So, the permutation matrix PGT corresponding to the real matching between the two graphs can be recorded during slicing. We train the model by minimizing the cross-entropy loss between the affinity matrix P and the true permutation matrix PGT. After getting the matching results, we average the initial feature vector similarity between the matched vertices to get the final graph level similarity. Finally, based on the obtained similarity, the target functions are sorted in descending order, and then the top-ranked target functions will be audited. We evaluate our approach from two aspects, effectiveness and efficiency. When setting K2 to 25, that is, in the second phase, audit the top 25 candidates for each seed. 31 unknown bugs in 5 real open-source projects were detected and confirmed by the developers. Taking these 31 bugs as the benchmark, we set up 5 groups of methods for comparative experiment, 4 of which are other code similarity-based bug detection methods, and the last one, HSE-, is the HSE model without the attention mechanism. Experiments show that with different K2, HSE can always achieve the highest recall rate. Here is the list of the 31 bugs we detected. We get some noticeable findings. First, the optimal vertex matching methods, that is, HSE and HSE-, discovered 27 out of the 31 bugs when K2 is 25. In contrast, under the same setting, the graph level matching based methods can only report 22 bugs, and the set matching based methods report 19. Second, 25 bugs get the highest rank by HSE and HSE-. In particular, 13 of them are ranked top 1. The higher the ranking, the easier to hit the bug during auditing. In other words, our method makes the bug stand out to be discovered. Besides, one of the bugs was detected cross-project, that is, a bug in ImageMagick was detected using a bug in mRuby as the seed. We also applied the rule-based static detection tool, Vertex, to scan the same projects, and none of these 31 bugs were detected, which indicates that the research on bug detection methods based on code similarity measurement is necessary. At the same time, the target in the motivating example described earlier, applying the HSE model, can be ranked 12th and can be easily discovered by the auditors. We also evaluate the efficiency improvement brought by the filtering phase. K1 is the number of candidates retained in the first phase. The larger the K1, the higher the recall, but the running time will also increase. On the contrary, the smaller the K1, the lower the recall, but it can significantly improve the efficiency. When K1 is 1000, all the 31 bugs will get into the second phase. It takes about 11 seconds to complete the optimal vertex matching of these 1000 candidates, while the filtering phase only takes 7 seconds, and the total time cost will be reduced by 94%. If we choose a smaller K1, such as 200 or 100, the recall rate will be slightly reduced, but the detection speed will be further accelerated. It will only take 11 seconds to perform a query, which is comparable to the speed of other methods used as comparative experiment in this paper, but can obtain better bug detection results. In conclusion, we propose a bug detection method based on code graph similarity measurement. The influence of the noise code can be effectively suppressed by optimal vertex matching. We design a two-phase strategy to accelerate optimal vertex matching to avoid solving an NP-complete problem. Two embedding models are designed to get an approximately but accurate enough optimal vertex matching. As a result, our method can be applied to a large-scale code base. We detect 31 confirmed unknown bugs in 5 real-world projects with the proposed method. Thanks for your listening.